In this lecture, we will cover moderated multiple linear regression. Now, as the name implies, this is a specific form of multiple linear regression, which means that we have two or more predictor variables, and in this case, one of those predictor variables can be treated as what we call a moderator variable, hence the name moderated multiple linear regression. So in this lecture, we'll start with an overview of what moderated multiple linear regression actually is and what it means, and then we'll go over the statistical assumptions underlying moderated multiple linear regression, which just so happen to be the same ones as multiple linear regression. And then we'll cover statistical significance and practical significance in the context of moderated multiple linear regression. So let's start with that overview. So moderated multiple linear regression, as I mentioned, is a specific type of multiple linear regression in which the effect of a predictor variable on the outcome variable is conditional upon the level or value of another predictor variable. And this other predictor variable we often call the moderator variable. Again, hence the name moderated multiple linear regression. So a moderator is simply a variable which a relationship between other variables is conditioned. So in other words, it's a conditional variable. So let's say the relationship between x and y is conditional upon the level of variable z. That would be z as a moderator variable. Now, a moderator variable can be continuous or categorical in nature. It's a little bit more straightforward sometimes with interpretation when something is truly a categorical variable, and the moderator can be interpreted just at discrete levels of that variable, especially if it's dichotomous, such as male versus female, man versus woman, and so forth. So let's think about moderated multiple linear regression in a little bit more detail using this data visualization to understand why we might use it and why it's important and what it can tell us. So let's imagine we have variable x, which is our predictor variable, and we have variable y, which is our outcome variable. And here we see a scatter plot. We can see that there generally is this upward trend here. And so we might conclude, based on a simple linear regression between x and y, that in fact there is a statistically significant and positive relationship between x and y, such that as x values increase, y values also tend to increase. Now, let's now throw in a little bit more information here. So let's throw in a third variable here that let's call z. So z is going to be our moderator variable, and you can see that there are two different levels for moderator variable z. There's level 1, which is represented by blue, and level 2 that's represented by red. And as you can see, now we have those same scatter plot dots, except now we can see which ones correspond to red and which ones to blue, where red again is level 2 and blue is level 1. And so our question is, would a standard regression line, a single regression line to represent the relationship between x and y, would that work as well when we now have this additional information that is coming from the moderator variable z? And so what we can see here is that actually, perhaps if we run this regression model, we'll find that there's really two different lines of best fit here. In other words, the relationship between predictor x and outcome y is conditional upon the level of moderator variable z. And so you can see that the relationship for level 2 of moderator variable z with respect to variable x and y is more positive or in turn than the variable for x and y at the level 1 of moderator 0 here. And so level 2 is represented by that red line and level 1 is represented by that blue line. So blue is a little bit weaker or a less positive relationship than the red. So again, this can be some hidden information that resides within our data. And so sometimes we want to ask these what if questions, or maybe it depends questions, which is another way of thinking about a conditional relationship here. So again, this is a very simple example of moderated multiple linear regression, but hopefully it gives you an idea of why this can be valuable. There's more information, and sometimes we can gather more understanding and better explain a phenomenon of interest if we measure and actually analyze moderator variables as part of the analysis process. So when you hear moderated multiple linear regression, you hear that term moderator, well, also think about this term, interaction. So a significant moderating effect can be referred to as a significant interaction, sometimes called an interaction effect. Now, specifically, an interaction refers to an interaction term in the context of multiple linear regression. Now, an interaction term is the product of the scores for the two predictor variables for each case. In other words, it's the product of the scores for one predictor variable and one moderator variable for each case. Because remember, one of those predictor variables we can frame as the moderator variable. And sometimes this is really arbitrary and just is a matter of theory that helps guide us to which predictor variable we're going to frame as the moderator variable. Now, often though, if one of the variables is continuous, one of the predictor variables, and one is categorical or even dichotomous, as it was the example that we gave with moderator variable z, well, usually the dichotomous or the categorical variable lends itself more to being the moderator variable for interpretation reasons. So let's look at how we actually calculate an interaction term. It's actually a fairly simple process. So let's imagine that we have two predictor variables here, and let's assume that these have already been grand mean centered. And so more on what grand mean centering means in just a second. But as you can see here in this data table or in this spreadsheet or however you want to call it, we have our cases, which are the unique participants or employees in this case. So we have 6 of them. And then we have each case's respective scores on the predictor variable and the moderator variable. The outcome variable is not pictured here. And so, for instance, for case 1, they have a score of -3.1 on the predictor variable and a score of 10.2 on the moderator variable. So how do we calculate that interaction term between the predictor variable and the moderator variable? Well, it's actually pretty simple. All we do is we multiply for each case the person's predictor score and their moderator score, and that brings us to the interaction term score. So as you can see, for the first case, -3.1 for the predictor times 10.2 for the moderator equals -31.6. So the interaction term score for that person is going to be -31.6. And you can see we repeat this process through all the additional cases. So when you hear interaction terms, this is actually what we're doing. To create the interaction term, this is what's happening either automatically for us, depending on what notation we use in our statistical software package, or we can do this manually and create this ourselves. So when we're talking about moderated multiple linear regression, again, we're talking about multiple linear regression at heart because we're talking about 2 or more predictor variables in relation to an outcome variable. It just so happens that one of those predictor variables we can treat as a moderator variable. So for that reason, we're still talking about a linear relationship here where y, if we represent it in equation form or formula form, is going to be our outcome variable, and b sub 0 is going to represent in this notation our intercept value. B sub 1 represents the regression coefficient for our predictor variable x, and b sub 2 represents the regression coefficient for, let's call it the predictor variable that's actually our moderator variable z. And then the interaction term is represented as x times z, and we have a regression coefficient b sub 3 that is tied to that interaction term as well. And then the plus e at the end refers to any kind of residual error that we might have, or lack of perfect prediction, in other words. So as you can see here, as I note, that we really have the interaction term is simply represented as x times z, because as you saw just a second ago, that's what an interaction term is. It's the predictor variable score times the moderator score and its product for each case or each person in your data. Okay, so now let's talk about what I mentioned a moment ago, this idea of centering predictor variables. So in order to improve interpretability of the results and to reduce collinearity between the predictor variables and the interaction term, so part of this is because the interaction term is based on those predictor variables, one way to reduce the potential collinearity between those is to actually center those variables. And specifically, in this context, with a moderated multiple linear regression model, we use what's called grand mean centering. And we do this for any continuous predictor variable that will be involved in a potential interaction that we include in our regression model. So grand mean centering is simply subtracting the overall sample mean for a variable for each case's score on that variable. Okay, and I'll show you what this looks like in just a second. Now, we don't need to center the outcome variable, and we don't need to center a predictor variable that is dichotomous or binary in nature, in other words, categorical. Okay, so just for the continuous outcomes or continuous predictor variables do we need to engage in grand mean centering. Now, we want to make sure that we perform any grand mean centering or any centering of any kind before actually creating the interaction term. So first center the predictor variable and the moderator variable, if applicable, and then create the interaction term by multiplying scores for the predictor and the moderator variable together to create that new variable that's your interaction term. Okay? And so essentially what's happening, if you have two different variables, two predictor variables, one of which is your traditional predictor variable and the other one is your moderator variable, and you want to know whether or not there's an interaction between them, well, you're actually going to have three predictors in your model. As I showed you with that regression coefficient, you're going to have your predictor variable, your moderator variable, and then the interaction or product term, as it's sometimes called, because it is the product, between your predictor and moderator variable, and those are all going to be predicting the outcome of interest. So let's look at an example of how we actually grand mean center in practice. So here we have 6 cases again, so 6 unique, let's say, employees. And let's say we have their scores on the predictor variable here that are currently not centered. So these are the raw scores here. Okay, so we can see for case 1, the predictor score is 3.1, for case 2 it's 1.9, and so forth and so on. So if we calculate the grand mean for all 6 people, or however many cases we have in our sample for that predictor variable, in this case it happens to be 2.0. So it's just the arithmetic average here. Now we can then conceptually or actually do this, put that grand mean of 2.0 for each case into our table and add this as a new variable. It's not actually a variable, it's just a constant now that we're adding. But this can be a way that you can then do a further computation where you actually subtract that grand mean for that predictor variable from each person or each case's predictor variable scores. So as you can see for case number 1, we do 3.1 for the predictor minus 2.0, which is that grand mean for that predictor, and that is going to equal 1.1, which is our centered predictor. And we repeat that process for all the remaining cases. Okay, so another thing we want to touch on too is this distinction between unstandardized and standardized regression coefficients that we usually concern ourselves with, whether it's simple linear regression, multiple linear regression, moderated linear regression, or multi-level regression. It's always going to be something of interest. Now, for our purposes, unstandardized regression coefficients will often work quite well in terms of interpretability because we're interpreting them in their original raw state, so in the raw scaling of our predictor variables, moderator variable, and our outcome variable. Now, standardized regression coefficients simply means that we are just standardizing using standard deviation units of our predictor variables, moderator variable, and outcome variables. Now, you can use both when it comes to moderated multiple linear regression, and both I mean unstandardized and standardized regression coefficients, so you can use either. It really depends. They just represent same estimates or different estimates of the same relationships. So the associated p-values are going to be the same when it comes to unstandardized or standardized regression coefficients. The difference is just in how you interpret it. Okay, so let's talk about the statistical assumptions underlying moderated multiple linear regression. As I mentioned at the beginning of this lecture, they're the same assumptions for multiple linear regression. And the reason is moderated multiple linear regression is just another form of multiple linear regression, a specific kind of multiple linear regression. And so the assumptions are as follows. The cases are randomly sampled from the underlying population. The data are free of multivariate outliers. The association between the predictor and outcome variables is linear. There is no collinearity between predictor variables, or at least not a concerning amount of collinearity. Also, the average residual error is 0 for each level of the predictor variable. The variance of those residual errors are equal for all levels of the predictor variables, which is known as the assumption of homoscedasticity. And also, finally, residual errors are normally distributed for all levels of the predictor variables. So, given those statistical assumptions and assuming that they're in place so we can properly interpret and actually run our regression model and have interpretable results and meaningful results, we can now move on to that actual interpretation side of things, which is statistical significance. So assuming we're using null hypothesis significance testing and we set alpha to be 0.05, which is fairly conventional, and that is two-tailed, we would then conclude if something is statistically significant if the p-value associated with a regression coefficient is less than that alpha level of 0.05. Now, in this case, we are talking about potentially p-values associated with a regression coefficient that itself is associated with that interaction term, because that's usually what we're interested in when we run a moderated multiple linear regression model. Is first we want to look to that interaction term and determine whether or not that is statistically significant. If that interaction term is statistically significant, it'll point to the fact that there is some kind of moderating effect happening here. Now, it won't tell you exactly how to interpret that. That's a subsequent step that you need to do. And using often data visualization and line charts is a helpful way for interpreting this, much like the one I showed you at the beginning of the lecture. So what we are doing with the moderated multiple linear regression, and specifically with one of the regression coefficients, if the p-value associated with that regression coefficient is less than 0.05, we are rejecting the null hypothesis that that coefficient associated with that interaction term is equal to 0. In other words, we are concluding that that is a statistically significant effect. Now, because this is a multiple linear regression model, we also need to remember that we are statistically controlling for the effects of the other variables in the model. Okay, so if we're focusing on the interaction term, we are focusing on that interaction term while holding the predictor variable and the moderator variable that is also in that model, that also were used to create that interaction term, we're holding them constant, or in other words, statistically controlling for them. Now, if the p-value associated with that regression coefficient is equal to or greater than 0.05, then we would fail to reject the null hypothesis that the regression coefficient associated with that interaction term is equal to 0. And this would also be while controlling for the effects of the other predictor variables in the model, which includes that moderator variable. Now, in addition, we could use confidence intervals too around that regression coefficient. And if that regression coefficient confidence interval does not include 0, then we could also use that as evidence of statistical significance. Now, as a reminder, if alpha is set to 0.05 two-tailed, then the corresponding confidence interval would be a 95% confidence interval. And again, if that 95% confidence interval does not include 0, then we conclude that it is statistically significant. If it does include 0, then we conclude that it is not statistically significant. Okay, so let's assume that we did find a statistically significant interaction term. Well, what's the next step in terms of determining the effect size or practical significance of that interaction effect or moderation effect? So with a moderated multiple linear regression model, we can compare the fit of nested models to determine the incremental variance explained as represented by R squared. Now, the incremental variance explained by the interaction terms tends to be pretty small in practice. So although I put these rules of thumb below, that a small R squared value can be described as is about 0.01, a medium is 0.09, and a large is 0.25. Specifically, this is the incremental variance explained, or the incremental R squared value. We're unlikely in practice to find a very large incremental R squared value of 0.25. Often the effects tend to be more close to 0.01 in terms of variance explained. And so just as a reminder, R squared is a model fit statistic and an effect size that can be interpreted as the proportion of the percentage of variance explained in an outcome variable collectively by the predictor variables in the context of multiple linear regression, or in this case, the specific context of moderated multiple linear regression. Now, because R squared is a model fit statistic, we can compare the fit of that model that includes the predictors in their interaction term with a model that only includes the predictors and without that interaction term. So we can see if accounting for the interaction between those two predictors by adding that in as an additional variable, which is our interaction term, which again sometimes is called product term, if that interaction or product term explains incremental variance above and beyond the constituent components of it in terms of the predictor variables that were used to create it. And so this is a way of this is what we're doing in practice. And the R squared, specifically the change in R squared, which sometimes you'll see represented by the delta in R squared. So you can think of it as a triangle, the notation Greek letter for delta or change. Change in R squared being the difference in R squared between the two nested models I just mentioned. The one model has the interaction term and the two predictor variables, or the predictor and the moderator variable, and the other model that we're comparing it to just has the two predictor variables, or the predictor and the moderator variable. And so we're wanting to know, is there a statistically significant amount of incremental variance explained by this moderating effect? And if we do see a statistically significant R squared value when comparing these two models, then we can interpret that difference or that change in R squared as the amount of incremental variance explained, and that is our effect size, and that is our practical significance. We're talking about a moderated multiple linear regression model. So in this lecture, we covered what a moderated multiple linear regression model actually is. It's just a specific form of multiple linear regression, except we are looking at the interaction effect between two or more variables. In this case, we just focused on two or more predictor variables here. And it's important to remember too that we need to make sure that we create the interaction term, but before doing so, we need to make sure that we grand mean center any continuous predictor variables that are going to be included eventually in that interaction term. And again, the interaction term can be referred to as a product term as well, because that's really what it is. It's the product of scores from your predictor variable and your moderator variable. Now, we also cover statistical significance and practical significance in the context of moderated multiple linear regression. Now, to really test practical significance, we're often focusing on that incremental variance explained, which is where the r squared value, and specifically the delta r squared or change in r squared or difference in r squared value, comes into play. So this wraps up the lecture on moderated multiple linear regression.